Periodic trends 2, ionic radius. Now we're going to be taking a look at a different form of an atom called ions and what trends we can see on the table from them. And hope you like the little joke that's right here. You'll get maybe it a little bit more as we go along if you don't get it already. Okay, so first of all, we want to talk about exactly what are ions. And ions are simply atoms of an element that don't have equal numbers of protons and electrons. What does that mean if they don't have equal numbers of protons and electrons? It means that there's a net charge upon them. So an ion is really just a charged atom. And basically, how do atoms get charges? What are the possibilities of things that atoms can do? Well, they can either gain electrons, they can lose electrons, they could gain protons or lose protons. But the problem with those last two choices is that if you lost or gained protons, you'd be changing the identity of your atom, which is only possible in a nuclear change, and so that's not a possibility actually in this case. Atoms can't gain or lose protons to become ions. They can only gain or lose electrons. Which brings up one of my favorite jokes, is two atoms were walking down the street, and one atom said to the other, "I think I lost an electron." And the second atom said, "Are you positive?" I'll pause for a second while you laugh. Okay? So basically what we look at is then what happens when these two things occur. When atoms lose electrons, that means now they have more protons than electrons, so there's a net positive charge upon them. So losing electrons means a positive ion. And positive ions are called cations, as you see in red down here, cations. When atoms gain electrons, then there's more electrons than there are protons, so you have a net negative charge, which means you have a negatively charged ion, which is what we call an anion. So cations are positive, anions are negative. Well, how can we remember those two things? A couple different ways here that can help you to remember that anions and cations are positive and negative. Okay, first of all, let's think of a cation. And if we think of dead cats, you think of cartoon dead cats, not real dead cats. When you have a cartoon dead cat or a dead animal in a cartoon like Roadrunner or something, they have their eyes crossed. So if you think about a dead cat with a crossed eyes are positives. You have a cat, cation. Cations are positive. For anions, think of onions. Well, why think of onions? Well, onions make you cry. When you cry, that's negative. Plus, when you cry, your eyes are usually kind of squinty, right? So onions make your eyes squinty because you're crying. Onions equals anions. A couple ways you can think about remembering those. Well, as we take a look at why are ions formed, before we actually get to the trend, we have a couple ideas to talk about with ions themselves. Now, first of all, is why are ions formed? Very simply, ions are formed to gain stability. Ions want to be stable, or atoms want to be stable. And the only atoms that are stable to begin with are the noble gases. And the noble gases are stable because they have a full octet. Their outer shell is full of electrons. They have that full 8 electrons in that outer shell that they can have. And so being stable means having that full outer shell. And so atoms want to gain or lose electrons in order to get that stability, become that stable as well. So what kind of atoms will form cations and form anions? Well, let's start off with metals. We have two types of atoms, metals and nonmetals. Metals generally will have less than a half full outer shell. They have 4 or less valence electrons. So for them to get a full outer shell, they could either lose their electrons. Let's say they had 2 electrons. They either lose 2 or gain 6. Losing 2 is a lot easier than gaining 6 to get that full 8. And so they'll lose electrons. So if you have less than a half full shell, you're going to lose electrons. It's easier than gaining. And so metals will form cations. Nonmetals, on the other hand, will have generally more than half full outer shells. So to get a full outer shell, it will be easier for them to gain electrons than it was to lose all the electrons in their outer shell. So they're going to gain electrons to form our anions. So metals form cations, nonmetals form anions. Okay, so we're good so far in that case. But how many electrons will they gain? How many will they lose? Now, if we take metals as an example, let's say we have aluminum. Now, aluminum, as an example, has 3 valence electrons. Well, if it loses 1, it still isn't full, right? Now it only has 2 valence electrons, and a full outer shell is going to be 8. So what is it going to do? It's going to lose as many electrons as it takes to get that full shell. So their metals are going to lose however many valence electrons they have. and your charge is going to be equal to how many electrons they've actually lost. And so if you talk about the group 1 metals only have one valence electron, so they're going to lose that one valence electron to give them a 1 minus charge. On the other hand, if you take a group 2 method, like example in this case we have lithium, lithium has 3 valence electrons, 1s2, 2s1, only 1 electron's in the outer shell, that highest energy level, so it's going to lose that 1, giving a +1 charge or an Li+. Beryllium, though, is in valence, or is a group 2, so beryllium is going to lose 2 valence electrons, those 2 electrons from the 2s, because it's not 8 yet. And so it's going to have a +2 charge. Aluminum with 3 valence electrons would lose 3 electrons, and so on and so forth. Now, for most metals, especially for your main group metals, not necessarily true for your transition metals or your rare earth metals, those are special cases that we're going to look at later on. The charge of a main group, or most of our main group metals, is equal to the group number. And the group number is that Roman numeral we're going to see at the top of the column. Now, not all tables will have Roman numerals on there, but we'll talk about later on then some of those adjustments we make if we have a different table. Now again, losing those electrons means you're going to have a full octet. But when they lose those valence electrons, for example, up here again with beryllium, if beryllium loses those 2 valence electrons, the second energy level is gone. So our next level down is our full energy level in that case. Now, the same thing is true with nonmetals, except that nonmetals are going to gain electrons. They're going to gain as many electrons as they need to get their full set of 8. So their charge is going to be equal to how many electrons that they're going to gain. Fluorine has 7 valence electrons to start with. All the electrons in the second energy level, 2 in the S, 5 in the P, that's 7. So to get a full octet, it needs 1 more. So it's going to have a -1 charge because it gained 1 electron, F-. Oxygen has 6 valence electrons, so it needs 2 more. It's going to have a 2p4 instead, so when it gains 2 electrons, it's going to be a -2 ion. And so our charge in our nonmetals will always be equal to the group number -8. Again, if we have different numbers up there, not the Roman numerals, these are the Roman numerals again, then we'll talk about how exactly we get that value. But right now, we're going to pretty much worry about Roman numeral values. So group 7 for fluorine, and 7 minus 8 would be -1. That's its charge. Again, atoms are gaining stability by gaining or losing those electrons. They're getting that noble gas configuration. Okay, so on to then how do the sizes of atoms compare to ions? Because that's kind of important too before we get to the trends. What happens if we take the size of an atom and we compare it to the size of an ion? Well, again, we're going to start and split each one up. We'll do the cations and then do the anions. So cations are going to be smaller than atoms. Now why? Why would a cation, a positively charged ion, be smaller than an atom? Now remember, becoming a cation means you are losing electrons, becoming positively charged. And when you lose electrons, now you're going to have more protons in the atom than you have electrons. So each electron is going to feel more positive charge or more positive pull on it than it did in the atom. And so every electron is going to be pulled closer to the nucleus. Bigger positive charge means it gets pulled closer. And the more electrons you lose, the closer the remaining electrons are going to be pulled. Okay? Then if we go to anions, anions will be bigger than atoms. Now, that should be pretty clear why, because it's going to be exactly the opposite of the cations. When atoms gain electrons, now there's going to be a bigger negative charge on the atom, so there's more electrons than there are protons, so overall your electrons are going to feel less positive pull. That ratio of protons to electrons is going to be smaller. If they feel less positive pull, they're able to pull further away. There's less holding them, so they get further from the atom, they expand, and their atom gets bigger. Here's an example of lithium. Now lithium here we have our atom. Okay, we have 3 valence electrons, or 3 electrons and 1 valence electrons. Lithium loses this 1 electron, and so what's left is just these 1s electrons. Now notice we've lost an entire energy level. We've gotten smaller. And also these remaining 2 electrons are also being pulled closer to the nucleus as well. So our cation, the lithium plus ion, is smaller than the atom. Well, again, looking the other way around at our anions, with fluorine, fluorine has 7 valence electrons to start with. We put 1 more in to make the F-. Each of these electrons, and there's supposed to be 7 protons, there are 9 protons in here. I didn't put them all in, just put a positive there. These electrons are now feeling less positive pull than they did before, so the atom can get bigger. So anions are bigger than what the atoms were. Okay, now we've got a pretty good handle on what ions are and what ion sizes are compared to atom sizes. Now what about the trends? How does ionic radius change going across a period and down a group? We're going to start with across a period. In general, ionic radius is going to decrease left to right. Okay, why is that? It's basically the same thing we saw for atomic radius. We have more protons in the nucleus, so we're pulling those atoms, those electrons that are in the atom, closer together. Plus, if we take a closer look and we look at the metals, the further right you go across the column, the more electrons are being lost. The more electrons are being lost, the bigger the ratio of positive charge to negative charge is, the more pull those electrons are feeling, the closer they get pulled into the nucleus. So the metals are getting smaller as you work across the table. So when we get to the nonmetals, then our sizes go up. So we're getting smaller, 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 get bigger. Because remember, we're changing to gaining electrons, which expands the size of the atom. But as we go to the right, we're not gaining as many electrons, so our atoms aren't getting as big. They're gaining less electrons, so we're not expanding as much. We're not feeling as much less pull as you were with the atom before. So as we go across a row, ionic radius is going to get smaller. We can see that in this first table here. The brown is the atom size. The red would be the ion size. So lithium is bigger than beryllium as an atom. Beryllium has lost 2 electrons, so the beryllium ion is smaller than the sodium ion. Then the brown over here is the atom size, blue is the ion size. Then we get bigger, but we get smaller because we're gaining less electrons, and that holds all the way across the row. Now in the group-wise, we can see what's happening in the group-wise from this diagram as well. What's happening to the ion size going down the group? They're getting bigger. Why? Same reason that atoms got bigger, because we still have more energy levels, which are further from the nucleus. So we have in this diagram, in this slide, both going across a period. They're getting smaller because there's more electrons being lost by the metals, and so the electrons are being pulled tighter. And then we have more electrons being gained, so we're bigger. But as we gain less electrons, there's not as much positive pull, so we're getting smaller going across. And going down, we're getting bigger because we have more energy levels. So this is just another example of a table we showed like in our last lecture with our periods. You can see at the periods, these are our ion charges. The ion sizes are getting smaller as you're going across a period. And then each continuous row, like the top numbers here, those are the ionic radii of the groups. And so each element will be the group of going across the corresponding value in each row. This table is showing both atomic and ionic radii. So if you look at just group 2, lithium atom, lithium ion is smaller. Beryllium atom smaller than a lithium ion, beryllium ion smaller than a lithium ion. Okay? And as we go across, we see that happen. Carbon gets bigger as an ion, but the ions are still getting smaller as you're going across. So we're still seeing the same trend occurring. And finally, we can do our general table to show generally what's happening. In this case, we'll do decreasing ionic radius. And you notice that the trend is going to look exactly the same as it did for atomic radius. We say decreasing atomic radius, ions get smaller going across to the right and going up, except for the noble gases because again, they will not lose or gain electrons. So this is basically dealing just with everything but the noble gases. And that is the trend for ionic radius.